The next force that we are going to look at now on our list of forces is the normal force. Normal force. You can call it normal force or force normal, whichever way you are comfortable calling it. Normal force or force normal. Our symbol for the representation of our normal force, we use capital letter F, subscript capital letter N, like that. That's how we represent our normal force. We can also represent it as a capital letter N, like that. So the choice is yours. You can choose to represent our normal force as a capital letter N, like this, or you can represent your normal force as capital letter F, subscript capital letter N, like this, normal force or force normal. Now, I want us to have a look at this force, but what I want you to always remember is that the foundation for this force is Newton's third law. Newton's third law is the foundation of the normal force. The foundation of normal force is Newton's third law. Now, I want us to link Newton's third law with our normal force here. It will enhance our understanding of the normal force. Now, I want us to go back to what does Newton's third law say. Newton's third law if you remember very well, Newton's third law says that when object A exerts a force on object B, when object A exerts a force on object B will exert an equal but opposite force on A. It's all about action and reaction. When object A exerts a force on object B, what does object B do? Object B will exert an equal but opposite force on A. I want you to remember this Newton's third law because sometimes in the exam they can ask you to say, state Newton's third law in words, right? State Newton's third law in words. You need to remember when object A exerts a force on object B will exert an equal but opposite force on A. I want you to remember this. It means that we can illustrate this like a diagram where we have object A and object B. Now, when object A exerts a force on object B, we can call this one force of A on B. Object B is going to exert an equal but opposite force on A, like that. So we can write this as a balanced equation to say the force of A on B is equal to minus this. Remember, this negative sign is showing us the difference in direction now, to say that if force of A on B was going to the right, it means force of B on A is now going to the left. Force of B on A. Now, this is true regardless of the difference in sizes of the objects that are exerting a force on each other. You need to remember this. Even if object A is the earth and object B is yourself, no matter the difference in size between the earth and yourself, the force exerted by the earth on you is equal to the force that you are exerting on earth, regardless of the difference in size. When the force exerted by A on B is equal in size to the force exerted by B on A, but different in terms of magnitude. This is Newton's third law. I want you to always remember it. Now, it holds true regardless of the differences in the size of the object. Now, the third law holds true regardless of A. Newton's third law holds true regardless of A. The differences in size of the objects, the forces that are there exerting on each other are still the same. So, regardless of the differences in size of the objects. What does this mean? It means that if the Earth is object A and you yourself, you are object B, it means that the force that you are exerting on the Earth is equal in size to the force that the Earth is exerting on you, regardless of the differences in size. I want you to remember that, because the common mistake that learners do is to think that the bigger object is going to exert a bigger force on the smaller object. No, regardless of the difference in size of the objects, the forces that they exert on each other, these two objects, is going to be this equal in magnitude, equal in size, but only different in what? In direction. Now, the third law holds true also regardless of the state of motion. Regardless of the state of motion. Regardless of the state of motion of the objects. What do I mean by this? Let's say, for example, you are pushing a car. If you are pushing a car, you yourself, you are object A and the car is object B, the force that you are exerting on the car is equal in size to the force that the car is exerting on you, regardless of the fact that you and the car are moving, right? Remember, this was true even if the objects are stationary. When I'm pushing an object, right? When I'm pushing an object, if I'm object A and I'm pushing object B, when this me and the object that I'm pushing are not moving, right? The Newton's third law still holds. The force that I'm exerting on the object is equal in size but different in direction to the force that the object is exerting on me. But if I'm pushing a moving object, right? The force that I'm exerting on that moving object is still equal in size to the force that the object is exerting back to me. So Newton's third law still holds true regardless of the state of motion of the object and also regardless of the differences in the size of the objects. So you need to remember this. Now, how does Newton's third law link with our normal force? That's what I want us to have a look at now. Remember, we have agreed that our Earth is spherical like that, and our Earth is pulling all objects or is attracting all objects towards itself. If I am to come here now, and if I have a table that is seated on the Earth's surface like that, and I put a box on top of this table, right? Let me just put a different color for the box so that you can see it clearly. If I put a box, right, this is our box, this is a table, and this is our Earth here. I want you to look closely. Now, our box is being attracted by the Earth, right? Our box is being attracted by the Earth. Now, it means that the box is being pulled towards the Earth. The box is being pulled towards the Earth. The box is being pulled towards the Earth like that. Now, if we didn't have this table here, it means the box was going to continue moving until it hits the surface of the Earth. But now it means that this table is doing something to the box so that the box does not continue going down. There's something that this table is doing so that the box does not continue going down until it hits the surface of the Earth. Remember, from what we discussed in our previous course, we agreed that this box has got a force of gravity that is pulling it towards the Earth. So now, it means that this table now is exerting an equal but opposite force on the box. The table is exerting a force on the box, which is equal in size but opposite in direction. Now, this is our normal force. So this means that our normal force is a reaction force. What is it reacting to? It is reacting to our force of gravity. It is balancing our force of gravity. Now, so when the box is being pulled down by the earth, if the table was not there, the box was going to continue going down until it hits the surface of the earth. But because of this table now is exerting a force on the box, which is equal in size but opposite in direction. We have got a name for that force. This is the one that we are calling our what? Our normal force. This is the one that we are calling our normal force. This is the one that we are calling our normal force. Now, our normal force or force normal is balancing the force of gravity. That is the reason why the box is not moving up and down, because all the forces that are going up are equal to the forces that are coming down. So that is the reason why we also say our force normal is a reaction force. It is reacting to our gravitational force. So in this particular case, our gravitational force is the action force, and our normal force is the reaction force. Now, so we need to note that to say our normal force is a reaction force. Now, and our force of gravity is the action force. Is the action force. What does our normal force do? Our normal force balances. It balances the force of gravity, like that. I want you to remember that. So, what does this mean? It means that wherever we are going to find our normal force, it will be balancing the force of gravity. So, if we are to say that our table is object B and our box is object A, right? If our table is object B and our box is object A, we can come here and say the force exerted by the box on the table, the force exerted by the box on the table, right? What name do we give to this force? The force that the box is exerting on the table, we've got a name for it. This is our force of gravity. The force that the table is exerting, the force that the box is exerting on the table, the force that the box is exerting on the table is our force of gravity. Now, the force that the table is exerting on the box, we've got a name for this now. That's what we call our force normal, right? The force that the table is exerting on the box is now our force normal. And in this particular case now, because our box is not moving up and down, it means that the force that the box is exerting on the table is equal in size but different in direction to the force that the table is exerting on the what? On the box, like that. So the foundation of our normal force, is Newton's third law. The force that object A exerts on object B is equal in size to the force that object B exerts on object A. This is very, very important. Now, I want us to check the relationship that we have between our force normal and our force of gravity. It's important that we look at them. Now, it means that if the object is bigger, we have already seen when we looked at our first force to say that the bigger the object, the greater the force of gravity. And we are noticing here that the greater the force of gravity, the greater the what? Our force normal, because force normal is just balancing the force of gravity, like what we have seen from Newton's third law. Now, the bigger the object, the greater the force of gravity of that particular object. The greater the force of gravity of that particular object, we must also know that the greater the force normal on that particular object. Now, I want us to take it even further as we look at this particular relationship. The bigger the object, right? What does this mean now? The bigger the object, the bigger the mass. That's obvious, isn't it? The bigger the object, the greater the force of gravity. Not just the force of gravity now. The bigger the object, the greater the force of gravity, and also the greater the force normal. Now, this relationship, I want you to log it in your heads and remember it, because when we look at our next force, which is the force of friction, we are going to see how also it is related to our force normal. Those two have got the same direct relationship that we are seeing here. Already we have seen that our force of gravity is directly proportional to our normal force, and we are going to see also that our normal force is also directly proportional to the frictional force. This is going to come out clearly when we look at our third force, which is our frictional force. When we look at our third force, which is our frictional force, this relationship that I'm writing on the board will come out clear. What are we going to see when we do that? We are going to see that our force of gravity is directly proportional to our normal force. It doesn't end there also. We are noticing that our normal force is also going to be directly proportional to kinetic frictional force that we are going to look at as our next third force. See you in the next lesson.